everyone. It's okay. Can you see my screen?
Yes.
Hi, sorry for the internet connection. I'm Philip Yuan. I'm very glad to be here with you today, sharing your research, projects, and thoughts. I have received all of your papers and the pre-recording videos. Very well done, and congratulations. This year, with the theme Re-Anthropocene, Designing the Human in the Age of Human, it is right time for us to rethink the relationship between the human being, nature, and the planet, especially under the current COVID-19 circumstance. In the post-humanism era, when traditional craftsmanship and the industrial production are replaced by contemporary digital fabrication technology, the idea of machine intelligence is highlighted in the design process. Based on that, human-machine collaboration, the applications of digital tools and robotics are now limited to visualizations and the realizations of the conceived from the human objects, but can be involved directly to the creation process and become a source of creative in itself. Human is no longer the only author of the architecture project. Machine becomes part of the design subject, which form the new mix subjective in the creative process. I want to put forward several examples in like 2 minutes about what we have done in the past 2 years. So this is like the Chinese Garden new contemporary art. We position the new 3D plastic printing rockery in front of the natural format and the Taihu stone in the middle, and an artificial craft stone 100 years ago. So it's like a collage of different history in tradition scenarios, which present a new technology and also address itself into the tradition. So that is like a background. I want to start the rethinking on humanism in the Anthropocene. And this is like a new human behavior. We can play with this kind of new rockeries as a street furniture, which engage into the visiting process. In the last few years, we research different pavilions and which focus on a bridge. Every year we make a bridge. This is a 3D plastic printing bridge. The first year is around 1,500 kilo. And the first year we can stand like 5 people on this. This is the second year. We invited 2 former chair of MIT and the Pulitzer Prize winner Wang Shu coming here with us for the opening of the pavilion. So this is a 3D concrete welding, steel welding bridge. Can stand like 7 people on it. And the weight of the bridge is around 800 kilo. So that is like a higher performance compared to the past one. And goes to the 3rd year, which is last year. We use the 3D robotic steel welding and glass fiber and carbon fiber weaving. We can stand like 20 people on this 500 kilo bridge. So the upgrading iteration coming year by year, which have a higher performance based on the material intelligence and based on structural performance-based design. So that is what we test here in our research, in our projects. And this is a new form paradigm, which can give us the production and design process and goes to higher structural performance and the new beauty coming from the robotic fabrication. This is, I was invited as a visiting professor teaching MIT with Philip Brock, who is from ETH. And this is research on the vault structure as a scaffolding to support the bricks. So based on that, we can make a super big span as a pavilion, like 8 meters in a very short time. So the 3 layers of bricks can make a super big span. And afterwards, this is Philip Brock and me, we're standing on it, which has a very higher structural performance. And based on this kind of formation, optimization, and fabrication process, so which is embracing the tradition like a vault structure to a bright future. It's a structural performance-based robotic fabrication. Then after that project, last year, we constructed the project like this, 45-meter span, which only 3 layers of bricks, and also the 3D printing, scaffolding support the whole process, which constructed in 1 month and a half, which is extremely efficient and based on this kind of process. And this is another pivoting way, making the same project with 3D plastic printing. We use environment-friendly material and to print a new wall structure to support the certain weight of the building. And afterwards, you can see this is a whole process of a project we made in Wuzhen last year. I think the whole process is based on the digital construction field, which integrate different kind of new technology in one project, including the plastic welding, plastic printing, and brick mansion, and also with large span with structure. So the process to integrate the computation and digital fabrication made a bright future for us. To end this of my brief introduction, so today, based on the panelists, we subdivided the presentation into 3 topics. The first topic will be from material computation to digital fabrication. So firstly, I want to invite Jun Wong Yoon. Could you briefly present what you have done in your paper to all of us, please?
Okay. Thank you for introduction. I will also share the slide. Okay. So my paper entitled Thermal Shading discusses about the digital design and additive manufacturing using SMP, which is a shape memory polymer. Also, we assume to use those as climate adaptive building skin elements. So discussed the 2 prototypes in the paper were selected from a series of research projects to focus on design and fabrication of SMP with a flapping mechanism as shown here. And they are called as blade and swirl in our paper. These designs were selected due to its simplicity and one-directionality in reversing the closed shape into the open position. For rapid manufacturing and prompt feedback between design and fabrication, 3D printing was undertaken to fabricate SMP components. SMP with different glass transition temperature were tested for 3D printing and filament manufacturing with SMP pellets. However, to enlarge the printing size from 100 millimeter to 150 millimeter, 2 different manufacturing methods were tested and compared in the process. For blade prototype, different design variations were experimented for 3D printing and heat test to examine the influence of curvature and form onto the printing quality, workload, and shape recovery. In 3D printing with the MM3520, many recalibration processes were taken to achieve the successful setting. In the end, MM3520 showed a much more prompt response to the temperature and quicker shape changing. For swirl prototype, we conducted a series of trials for 3D printing with many errors and handling to achieve the final successful production as shown in the picture. However, in scaling up the model size from 100 millimeter to 150 millimeter, several issues were discovered to tackle. Without resolving problems by human surveillance and support, it takes 10 hours to print the 150 millimeter model, which is not really desirable in a rapid prototyping. To compare the manufacturing efficiency, we conducted the SMP resin casting experiments. However, the SMP resin models also showed more problems than 3D printing. Therefore, from experiments with 2 different manufacturing methods, it was demonstrated that 3D printing is superior to casting from its advantage of production time, required equipment, procedure, and consumed materials. This comparison informed us to revisit the system and design. In consideration of reversibility of the shape and complications in fabrication, the prototype was redesigned to have an SMP actuator with other flexible surface materials. The designed SMP actuators were simple and easy to be 3D printed. Throughout the whole processes from blade to swirl, from surface active to actuator system, the last prototype was the design which achieved the desired size and kinetic movements. From this study, we could review selection of fabrication methods rather than blind pursuit of 3D printing, in addition to verifying many challenges to overcome. To make the full
degrees Celsius as a controllable temperature range. The material reflects of two opposite properties of the plastic and textile by heat pressing. According to the change of the thermoforming thickness, the range of the plastic properties change from elastic to hard as the wood board. There are two processes of fabrications. One is winding fabrication, the other is thermoforming fabrication. And the winding pattern could make the units more flexible. And with the temperature controlling, the PET material could be shaped. The goal of the thesis is mass customization. For instance, it can change the angle to control the width of units.
And the other, without framework.
And with these two developments of each fabrication, I want to show you a video. Custom-made heating bar is used in the thermoforming process, which can control the temperature in two sets to be chosen. In a preliminary heating path test, I collect the relevant data such as time, mounting speed, the contact area of the heating tool, and melting degree of the nonwoven fabric. About the thermoforming coding, the first one is for the concave surface. In an effort to achieve the expected depth, it has to get more force interior to respond to the material rebounded. Therefore, the coding of the path is set up with a deeper parameter. The second one is for heating the boundary. In order to ensure the woven mesh and edge are mute, it takes a high temperature, repeated, and slow plate to operate. This is the process of fabrication. And this is our successful process of winding fiber and the product of the angle winding. After the final winding products are performed, different combination of winding patterns will produce different heating pressing effects. For the enhancement of product stability, it takes overlapping winding patterns with different thermoforming types. After analyzing the individual strands, it will be assigned to different parts of mockup by the stability of the structure. The bottom of the mockup takes a hard PET board with PET non-woven textiles by the robotic arm to stabilize the entire structure. Based on the concept of the circular economy, the thesis is conducted towards the goal of one material, one machine. And it means using a material but attaining more properties and performing multiple fabricate process by using one robotic arm. And this is my thesis. Thank you.
Thank you, John. I think it's a very interesting topic based on the thermoforming about filament winding process based on one material and one heating instrument. And material intelligence is really interesting to make a great performance to generate different kind of form. So I think we can have further discussion afterwards after the presentation. So next one, we will invite Celine Chen. Would you please share your screen? So John,
Yeah.
could you close down your screen and please. Is Celine here?
Yeah, I'm here.
Please.
Share. Hi, my name is Celine and I'm from Victoria University of Wellington in New Zealand. So I'm just going to do a quick summary of my research. So this research focuses on developing a workflow to create a self-supporting structure using robotic fabrication and computational tools. Parametric software combined with the robotic arm was explored to find how it can create timber connections to connect sheet materials at different angles. This method was utilized to repurpose the concept of sheet materials towards a complex structure, which adopted the idea of mass customization over mass production. Using this technology saves a lot of time compared to when connections are created manually in the past using woodworking techniques. Japanese timber connections were a strong influence for this research due to its prolonged lifespan and sustainable advantages. These connections did not require any metal fixings, making it environmentally friendly, so this is why they wanted to incorporating the technology we have today to use it. This research explores fabrication with the 6-axis industrial robotic arm. The use of a digitally controlled fabrication process broadens the boundaries which offer the opportunity to create complex designs and inform new construction techniques. So the ability of the robotic arm being able to cut at different angles, that the plywood can be joined on angles to create designs that isn't just a box shape. Instead of a limited choice of possible construction options, every surface can be customized based on design parameters. In this research, 5 sheets of 25mm thick plywood was joined together using a mortise and tenon joinery technique, and it was able to hold itself together without the need of any glue or screws. The creation of these panels broadened the understanding of bringing a design from the digital world to the physical world. So the panels were able to just slide in and lock together as shown in the video. Yeah, so that's just the overall structure that I made. Thank you.
Great.
That's the end.
Okay, thank you, Celine. It's great research on the timber panel based on different kind of a very precise, accurate fabrication process to generate different kind of geometry. I think a lot potential future based on this system. So next one, we want to invite Virginia, Melanick.
Hello.
Hi, Virginia. Virginia actually the PhD candidate studying Tongji University, and right now she is teaching as a lecturer in Calmanton University. So let's welcome Virginia, please.
Hi, so Philip already introduced me, and I'm going to really quickly present my project on sewing pneumatic forms. And I was really inspired by the body, and partially the call for this conference really dealt with human element in architecture. And we look at the body all the time when we are relating to proportions like the modular man or Neufert's graphic standards, but the body is also really integral when we think of fashion design. So under here, you can see measurements of the body for fashion design are slightly different than those we consider in architecture. And then also in art, the body is really defined a lot by the textures and the wrinkles of our skin. And artists have always been very fascinated with hands and these kind of very intricate details that are within them. And so I was really taking this project to combine digital technology and traditional craft of dressmaking. And so I looked at the different sewing techniques that have been used for centuries in the manufacturing of dresses, and took these sewing techniques to help design in a 3D program made for fashion design. So this is Clo 3D, where you can take panels of fabric and assign stitching patterns and types of stitches. You can assign typical fabric and material qualities, and then add gravity so it drapes like it would drape over your body. But in this case, I also added a inflation physics analysis here so that it would start to inflate like a pneumatic form, which is the desired shape for an architectural structure. The program also allows for you to kind of manipulate and push and pull it the same way that you might be concerned about how a shirt or a dress might need to push and pull. But I was thinking of this in a more architectural sense of how we maybe touch or play with the different walls or spaces or furniture within our architectural environment. And then lastly, it also helps give simulation effects of where different moments of stress and strain are going to be based on the stitching and how the fabric is being pulled. So it's really helpful in this design process. Here you can see my resulting patterns of the 3 different designs, which each focused on an individual sewing technique from the dressmaking. And then resultantly they became these kind of blobs, but I was much more interested in the textures that they created and how the human body can interact and engage with these textures as we're looking at this age of the human and how these days people are actually very socially isolated. The artist Lucy Mcrae, her work was really inspiring to me in a sense that she's looking at the fact that we have a sort of touch crisis due to everybody being addicted to their phones and their computer screens. We no longer hug and embrace one another, and she creates work that simulates hugs and gives comfort to people, and there's a lot of science behind why this is beneficial. And so I was hoping through this exploration to take advantage of those experiences into our architectural environment. Thank you.
Thank you, Virginia. It's a very interesting permanent research. I think we can make some discussion after all the presentation. I hope we can have like 10 to 15 minutes to make further debate or discussion on different kind of material computation. So it is a body architecture, which is very different scale compared to the others. So the second topic, I want to go to the structural performance-based fabrication. And in this session, we invited 2 panelists who participate today, and also the other 2, we want to present their videos. So as to the second topic, structural performance-based digital fabrication, we want to invite Uri Shi. Is Uri here? Uri Shi? Could you present your paper? Uri?
Yeah, I'm here.
Okay, please.
That's me. Can you view my screen?
We can see you, but not your screen.
Just a second. And now?
Yes, here we go.
All right. So this is a research on funicular structures using topological assemblies done by Aisha Fida, who is in the audience room right now. That's why I put the picture again. It's a joint work. So what we attempted here is to, the aim is to achieve the ease of assembly and dismantling of funicular structures using topological assemblies. And what we were trying to achieve more than what's being done already in these lines with this kind of robotic stone cutting construction by the lab, the Italian Morpho Structure Lab, is to limit the customization. These are the 2 goals, because we sit in the context where we really are refrained from using the robots as a cutting edge technology in the real-time constructions on site, because it's unaffordable. It is to minimize the cost and minimize the scaffolding, so that we can actually take these kind of construction on site in today's time. So what we did is, amongst the topological assemblies, which are force-locked elements in a given plane or in a 2-dimensional plane, which is the osteomorphic blocks, a block is designed based on the sine-cosine trigonometric function, and when we flip it, it locks. So further, when we apply it into a curve geometry, of course there will be a level of customization required. If it was a plane, it was the same block which can be flipped and can be locked. But when it is curved, there are these three modules, which is anchor spacers, one at the base, and the keystone. Now these three elements are going to change based on the geometry. So based on the rise and span of the structure, it is going to always customize. Once again, except for the catenary arch and barrel board, where we are almost able to achieve 68% of the customization limited. That means we are really able to balance between the standard and customized module. The structures like this, where we have two linear spans and then we let the form to take shape as funicular structure, or with the four side linear supports, the level of customization, of course, is going to increase. So how we visualize the construction logic is
Two methods of
something like
construction
this.
were visualized. One with minimum formwork and the other without formwork. For symmetrical form having a square plan and four linear support, the assembly begins from the outer edge having two parallel supports for the first arch.
So with these construction options, like if we have the first one starting at the with a minimum formwork on site with alternate blocks interlocking, the next rows can be assembled without any formwork. And before we start the next row, we have to secure the first row with the tension cable tightened fully and secured with that. So this also helps us performing in the lateral loads. So likewise, we are able to make this system not only robust in interlocking in one direction, but in all the directions. So finally, what we are achieving so far is we are able to do a dry construction, which is self-supporting using minimum scaffolding. With the extra dose post-tensioning system, it makes it withstand the lateral loads and vertical upliftments. The modules are assembled and disassembled as required. That means we can transport them as and when required to whichever site, and it can either be called temporary or emergency shelters. The cost of construction and time are optimized because obviously if we are not having all the customized blocks, which questions definitely in the domain of whether we are going for a highly sophisticated 100% customization, or we are going for a balanced system which is affordable. Finally, the customization is reduced to 68% for barrel balls and 45 to 55% for the symmetrical funicular forms. Now, what we are going to work further is on the material of these blocks in real time, test them, and how much can we really push this for the free-form geometry. Thank you, Philip.
Thank you. It's a great research. I think what you're doing is focus on the new formation tools by the different kind of vault, like Rhino vault, like different kind of formation, and which based on the modular geometry form finding fabrication process. I think the modular definition will give a great opportunity in the fabrication process, and which is totally based on the structure performance-based tools. I think it's really meaningful to, especially working on the asymmetrical funicular vaults, that is a super high performance structure And we also make a lot of research on that. So I find your research is really interesting and goes through the high efficient structure system, which has a great potential in the future. So thank you so much. So next, I would like to invite Liu Yige, who is just got her PhD from Tongji University, and right now want to go to Southeast to start her postdoctoral study. And she actually working a lot on the filament winding project. And let's invite Yige to present the project.
Hi everyone, I'm Yige Liu. I'm from Tongji University. Our research is on knitted fabric reinforced composites based on advanced knitting, and we challenged ourselves to design and build a self-support tower with this very potential new architecture material. And for this project, we developed a structure performance-based computational workflow based on advanced knitting. This workflow covers 3 aspects from design to fabrication and corresponds to the challenges at the macro and micro scales of the material system. With this workflow, we developed a structure form through comparative study, which can maximize both the tower's local and global stability, while the material thickness is only 2 to 3 millimeters. And also in this workflow, we are able to inform the distribution of structural elements such as reinforcements and holes according to the structure information through topological optimization and finite element analysis to optimize the force flow. While designing the structural elements of knitted preforms and steel plates, we also consider the logic of knitting and fabric connections so as to make them easy for fabrication and assembly. It is worth mentioning that during this workflow, we developed a program that can automatically convert 3D geometries as well as structural design information into a digital model of knit stitches and generate G-codes for the CNC knitting machines. This program established a smooth connection between knitting, CNC knitting, and architecture design. So based on this workflow, we finally achieved a 7.2 meter, 260 kilogram self-support, lightweight, stable tower. The knitted composite tower uses a minimum mass of material to achieve the effective structure and minimizes material wastage during the whole process. This knitted composite tower verifies our structural performance-based computational workflow based on advanced knitting and demonstrate the design potential of knitted fabric reinforced composites for super lightweight and high performance architectural applications. And for future research, we will further improve the workflow to reduce the problem wrinkles, and we will also improve the knitting code generation program to make it fast and robust. And that's all about my presentation, and thank you.
Thank you, Yige. It's a project we achieved last year. I think it goes through the super high and super thin, ultra thin knitting project, give a super high performance-based formation. I think this methodology, the whole working flow, is based on not only the material intelligence research, but also we integrate the structure performance-based design and the knitting fabrication technology. So we can make maybe further discussion later. So next, we have 2 presenters who are not here, Xiaokai and Liu Chenjun. I will invite my, are you here, Xiaokai? Yeah, please.
Hello everyone, my name is Xiaokai. Here we take a pavilion as an example to discuss the design and the fabrication methods of aggregation based on workcell. Workcells are also known as 3-dimensional pixels, and their basic shape is a cube. It's a way of representing space in numbers. In order to increase the complexity of the aggregation structure, we decided the workcells of 6 different sizes. The bigger 3 will be the main parts of the workcell system. The small streets are used as incidental parts of the voxel system to reduce self-weight and increase the structural strength. After defining the shape of the voxel, we think about how to design the aggregation unit within the voxel boundary. We take into consideration of the materials, the intersurface of connection design, the weight of fabrication. In this study, the units are connected by the surface-to-surface connection, which is a stable way. This diagram shows the process of 6 units from initial design to fabrication design. The next step is to take a further study on how to design a voxel system. There are 2 ways. One is to transform the existing form into a form composed of voxels through the top-down voxelization method. The second way is the main point of the research. It is a bottom-up design process. In the design of the pavilion, forms of force and the support points are defined. The reasonable field is found in the space, as shown in the figure B. The new field controls the boundaries of the aggregation generation. After complete the aggregate the 3 larger size units, the small size units are used to replace the larger units that are not the main part or to add the vulnerable part of the structure. This study provides a general design method of complex aggregation structures. The change of voxel shapes makes the aggregation more diverse.
Okay.
In this paper, a method of combining performance-driven optimization with parametric design is proposed. The iterative evolution is under the control of performance loop and fabrication loop, which makes all the data provided by parametric design in a practical project available for exploring structural analysis and digital prefabrication. The practical project is located at the Fujian Children's Hospital in China. In the process of project evolution, a prototype is controlled by 2 factors: structural performance and prefabricated construction, by setting 2 conditional optimization statements in the original shape design programming. In the loop of fabrication driven, which shows in the screen, the data stream flows from point cloud to the final layer data through 3 self-programmed script plugin, whose function is linear selection, constraint, adaptation, and deliver layered construction data. In the loop of performance driven, the data stream flows from line data to the final component data through 2 grasshopper plugin, whose function is statement, intuition, and dynamic evolution. After the previous stage of design, selection, and performance optimization, the whole curve steel frame gradually becomes a multi-level frame system, customized and codified under the parametric form. All steps of the project before the real prefabrication production can affect interactively and change in linkage, which provides efficiency and accuracy guarantee for project coordination and adjustments. The basic geometry is used to generate systems such as film, aluminum plate, and glass, creating a group of shape types linked under the guidance of the main system steel frame data. During the stage of steel prefabrication, the construction component is shaped by a series of CNC machine systems. In the whole process, the entire building is designed, optimized, and built using digital system of 0 and 1, that representing behavior signal, and the operational monitoring of the building is closely related to the initial 0 and 1 in the future. Thank you.
Thank you for the two presentation. I think Xiaokai and Liu Chenjun is very interesting, goes to two different directions of data fabrication based on structural performance. Xiaokai goes to like the pixelization. I think it's a discrete, totally discrete system. And the voxel modular gave simulation to different kind of geometry surface, while Liu Chenjun goes to a different direction. Liu Chenjun is making this kind of 3D banding in steel structure, which goes to this kind of continuous and to simulate different kind of curve and make the accuracy process to make the fabrication work. So that's very interesting two direction. So we can make further discussion in the final panel discussion. And I would like to go to invite you goes to the topic 3, which focus on topic of workflows of computational design and digital fabrication. So firstly, I would like to invite Xiao Zhifu Xiao. Would you like to present right now?
Hello?
Hi.
Oh, okay. Because I got a little code, so I asked Google to help me to pronounce the voice. And wait a minute, I will show you the...
Okay, no problem.
To share this new approach to digital fabrication workflow with you. We regard digital fabrication workflow as a seeing, moving, seeing design thinking model, as Sean and Wiggins had indicated in 1992. Furthermore, Wesug also confirmed Sean and Wiggins' hypothesis and proposed ISCW system so that remote participants can interact with each other. In 2017, Ling Xie improved this seeing, moving, seeing model as an automatic drawing generation system, DFA, to help fabrication team to assemble complex components. We then improve ISCW and DFA with interactive coexisting system to aid armature team crew manage fabrication process between virtual database and physical fabrication environment. We practice a coexisting digital twin concept to enhance a recursively, automatically, rapidly exchanging process. We build digital twin system where users can wear mixed reality device as a visual sensor and constantly update and cite physical changing onto the cloud database. We implement this mixed reality interactive data flow as a coexisting fabrication system and called it as CoFabs. CoFab's data flow is composed of 3 threads. The first one is the stage of sensing physical prototype changing. Another one is the stage on premises virtual cloud database. The third one is the processing stage, which deals with the gesture in the digital model rendering. To figure out how to use this interactive interface to aid users in making decisions, first, we upload the digital twin model to database and render a mixed reality environment in HoloLens. We renders each digital node via having 4 understandable color modes to help team leader recognize the working progress. Under fabrication process, we discovered that the weaving structure morphs via different texture strength. Thus, we add a variable parameter pa to express the degree of bending of the material as the table shown on screen. Inputting this parameter helps us identify the most reliable design decision, and users can use the same gesture to move the node. We appreciate the time you took, and please follow our website, idf.tw, for further investigations.
Great. Thanks a lot to Chifu. I think it's a great research based on digital twin methodology. and especially focus on the node vector, and which give a very strong material intelligence to generate different kind of form. So thank you so much. And next, I would like to invite Niels Martin Larsen. Is Niels here?
Yes, I'm here.
You're from Denmark, right?
Yes, that's correct. I'll try to share my screen.
It's really early morning.
Yeah, it's really early here. Can you see the slide?
Please.
Okay. Yes, I'm from Aarhus School of Architecture in Denmark, and I did this paper with Anders Kruse Åger and Lin Hyun Kiefer. It's called Digital Workflows for Natural wood in construction. Okay, let's get started. Human behavior change the ecosystems of the earth. To build, we excavate, mine, harvest, and transform large areas of land. And the consequence is the creation of biological uniformity, dying species, and the vast regions of monoculture. The timber industry is oriented towards standardization, that is strict equal-sized materials, and the best way to obtain such specifications is through plantation with straight-grown trees, as you see here. However, plantation forestry impacts biodiversity, and the current practice of timber production is often degrading the forests. So to be able to position wood truly as the sustainable resource for buildings, the current industry would have to change. And so we have been seeking to rethink the way we use timber in construction and look at the possibility of using crooked trees to allow for better use of resources and possibly new types of forests with increased biodiversity. So our concept is to match natural saw logs, which are crooked, with geometries and extract machining information so that natural shapes of the logs can be used in different construction types. Yes, so the method consists of a series of steps. The first step is to establish a database of saw logs. Each saw log is scanned and analyzed into a NURBS representation, which is saved with information about location, quality, species, and dimensions. An overall design solution is defined, and here we see a lamella roof structure, which we're working with at the moment. And then customized scripts. We have been developing scripts that then distributes the material in the structure. I'll get back to that shortly. And of course, toolpaths for the robotic fabrication of each member is generated, and we use motion capture technology for positioning the logs during fabrication. So a little bit more into the data handling. The point cloud from the scanning of the saw log is translated into rationalized geometry. So the main task is actually to define a center curve, since this is used for the selection and placement of the logs. Also tool path generation and visual representation. And then the center curve plays an important role in generating the NURBS surface as well. So the system will go through each member of the structure and compare the curve segment with the center curves of the logs in the database and find the best match. So the log with the smallest deviation from the center curve is selected. We've been testing different types of robotic machining, and here, as you see here, we are using milling at the moment. We also experimented with bandsaw, which we might come back to. And here you see one of our latest prototypes. We've been testing the design of the joints and the transition between the components, which we try to make as smooth as possible, of course. And here in the fall, we will actually produce a small test building at an open-air museum with this fabrication method. Thank you.
Thank you, Niels. I think it's a great presentation to ending this session, because I really like what you're doing, which not only integrate the machine intelligence and artificial intelligence into design process, but at the same time, you can see still the humanity in your design as well. I think this kind of natural logs gives the strong materiality, which can to help us to imagine how to make a full use of the environmental friendly material like the logs and timber, and how to make a full use of them into the different kind of form That's really a smart design process based on the fabrication technology. So because of the time limitation, we have too many panelists. I should end this session, but I'm looking forward in the future. If you have any other special opportunities, I would like to invite you to give lectures in different kind of platform. We should learning from each other. So thanks a lot for your presentation. Thank you to all the panelists. Thank you so much. Bye-bye.
Thank you.
Thank you.